Hey everyone, and welcome to This Explainer. Today we are going on a seriously mind-bending journey through space and time. You know, whenever you look up at the night sky, you might wonder what's really out there. Well, we're going to discover how looking out into the sheer vastness of the cosmos is, quite literally, looking backwards in time. We'll be using some absolutely incredible imagery and data from NASA to understand exactly how the universe's sheer scale fundamentally changes the way we experience reality. Let's get into it. Okay, let's kick things off with a totally wild question. What if the telescopes we use, powerhouses like Hubble or James Webb, aren't just giant magnifying glasses, but actual time machines? I know, it sounds like pure science fiction, maybe something straight out of Doctor Who, right? But it's an absolute scientific fact. By simply gathering ancient starlight, these instruments allow astronomers to witness ancient history unfolding right before our very eyes. But to really grasp how a telescope can look into the past, we first have to talk about the universe's ultimate speed limit. So, to wrap our heads around this time travel, we need to define a term you probably hear all the time: the light year. Now here's the catch. Despite having the word year right there in the name, a light year is actually a measure of distance, not time. It represents exactly how far light can travel in 365 Earth days through the vacuum of space. Because space is just so unfathomably huge, measuring things in standard miles or kilometers, that stops making sense real quick. To give you a sense of the crazy scale we're talking about, consider this. Light zips through interstellar space at an absolutely staggering 186,000 miles per second. Think about that for a second. At that speed, you could orbit the Earth more than 7 times before you even finish blinking. When you stretch that incredible speed out over an entire year, light covers almost 6 trillion miles. So when we say a star is 1 light year away, what we're really saying is it's 6 trillion miles away, and its light took 1 full year just to reach our eyes.
Moving right along to Section 1. Our cosmic neighborhood.
Let's start our journey close to home, right here in our local cosmic backyard. The light travel times here are relatively short compared to the rest of the universe, but they're still pretty mind-blowing when you think about our day-to-day lives. Even within our own solar system, you're constantly looking into the past. Our sun is 93 million miles away, which means it takes light about 8 minutes to cross that gap. So when you step outside and feel the warmth of the sun on your face, you're actually interacting with sunlight that left the solar surface 8 minutes ago. If the sun were to just suddenly vanish, which, don't panic, it won't, we wouldn't even know about it for a full 8 minutes. Look out toward Jupiter and you're seeing it as it was over 43 minutes ago. And if you somehow traveled at light speed all the way to the Oort cloud at the very edge of our solar system, it would still take you almost 2 years. You see? You're always looking into the past.
Now, moving just a bit outside our solar system, we hit the very next star over. Our closest known exoplanet neighbor, Proxima Centauri b, is perfectly highlighted here. It's located about 4.24 light-years away from Earth. That means the starlight we capture from this system right now actually left it over 4 years ago. Even if we built a futuristic spacecraft capable of flying at the absolute speed of light, it would still take us over 4 years just to get there.
And man, what a strange world Proxima b is. It sits in what we call the habitable zone, meaning it might have the right temperatures for liquid water, but it is vastly different from Earth. We take 365 days to orbit a nice yellow sun, right? Well, Proxima b whips around its star in just 11.2 days. It orbits this volatile little red dwarf star that's known for releasing these powerful bursts of radiation. Plus, because it's so close to its star, it's very likely tidally locked. That means one half of the planet permanently faces the star in this perpetual blazing daylight, while the other side is just frozen in endless night.
All right, Section 2, inside the Milky Way.
Let's aggressively scale things up and venture deeper into our home galaxy, the Milky Way. Out here, our distance measurements shift dramatically. We're no longer talking about a few years, we're talking thousands and tens of thousands of years. Our galaxy is this massively complex rotating spiral of gas, dust, and hundreds of billions of stars, and it spans roughly 100,000 light-years across. Just try to wrap your head around that for a second. If a pulse of light flashes on one far edge of the Milky Way, it's going to take 100,000 Earth-years just to travel to the opposite side. All those dark, patchy areas you see are giant clouds of dust and gas that actually block starlight. Those massive clouds are dynamic cosmic nurseries where stars are constantly being born and where old stars go to die.
So the absolutely crucial point here is that because of these unimaginably vast distances, we are frequently looking at stellar ghosts. Massive stars go through these incredibly intense, dramatic life cycles. Over millions of years, they ignite,
They swell up into red giants, they shrink down into dense white dwarfs, or they just violently explode as supernovas. But here's the crazy part. Because their light takes so long to reach us, a star could completely die, but its original light, the light emitted back when it was young and vibrant, is still out there, traveling through the cosmos toward our telescopes.
This timeline really puts that delay into perspective. So we already know Proxima Centauri's light is just over 4 years old. But look at the red supergiant star Betelgeuse. The light we see from it tonight is 700 years old. Or consider the Crab Nebula, which sits 6,500 light-years away. In the year 1054 CE, Chinese astronomers recorded seeing this brilliantly bright guest star in the sky that was so luminous you could actually see it during the daytime. They were witnessing a violent supernova explosion. But get this, that star didn't actually explode in 1054. It exploded 6,500 years prior, all the way back around 5400 BCE.
Actually, let's jump back to Betelgeuse for a second because it is such a fascinating example of this. Back in the fall of 2019, astronomers noticed that Betelgeuse was dimming significantly. Thanks to Hubble, they figured out the star had basically blown its top in a massive surface ejection, throwing out a huge dust cloud that blocked its own light. Now, because the star is nearing the very end of its life, scientists believe it's on the verge of going supernova. In fact, it is entirely possible that Betelgeuse doesn't even exist anymore. It could already be dead. But because its light takes 7 centuries to reach us, its ghost is going to keep shining brightly in our night sky for hundreds of years to come.
Which brings us to Section 3, the deep cosmic past.
Now let's leave our galaxy completely behind and travel out into the deep cosmic past. Out here, the light we capture has been voyaging not for centuries, but for millions and even billions of years. The scale just escalates incredibly once we step outside the Milky Way. This sequence right here takes us all the way back toward the very dawn of time. We start at 2.5 million years ago with our nearest galactic neighbor, step back nearly 13 billion years to an ancient star, and finally arrive a staggering 13.4 billion years into the past, placing us just 400 million years after the Big Bang itself.
Think about this. When you observe the Andromeda galaxy, you are staring at light that left its source 2.5 million years ago. We're talking about Earth's Paleolithic period, back when early humans were just figuring out how to make stone tools. Then we have Earendel, which is the farthest individual star ever detected. We can only even see it because a massive cluster of galaxies between us and Earendel acted like a giant cosmic magnifying glass, a really cool process called gravitational lensing. That star lived a brief, fiery life and died over 12 billion years ago, yet Hubble still caught its lingering light. And then there's GN-Z11, one of the most distant galaxies we've ever observed. Because we're looking 13.4 billion years into the past, we are getting a literal sneak peek at the universe in its absolute infancy. We are watching the starting line of cosmic evolution.
All of this brings us to a quote that I think perfectly sums up everything we've explored today. At its core, astronomy is really just archaeology. I mean, it's spot on, right? Just as an archaeologist digs into the Earth to uncover artifacts from ancient civilizations, astronomers point telescopes up into the sky to gather ancient, traveling light. It just beautifully illustrates how telescopes are the ultimate tools for uncovering the universe's long-buried history, allowing us to piece together the magnificent, sprawling story of the cosmos.
So, the next time you step outside on a clear, dark night and gaze up at that huge canvas of twinkling stars, take a second to remember the incredible journey of the light that's hitting your eyes. You aren't just looking off into the vast distance of space. You are staring directly into the deep, magnificent past. You, my friend, are a time traveler, taking in a panoramic view of cosmic history. I want to leave you with this one thought. When you spot a star in the sky tonight, ask yourself, are you seeing something that is actually there right now, or are you just admiring a beautiful ghost? Thanks so much for joining me on this explainer. Keep looking up and keep wondering.